Welcome everyone to another installment of AAAR's lecture series where we get to hear from authors of notable journal articles from aerosol science and technology. Today's talk is hosted by AAAR student chapter at University of Florida. And I'm going to turn it over to Azad Madhu, who's president of University of Florida's AAAR student chapter. Today,
Hello, everyone. Thank you. Thank you, Ryan, for the introduction. Thank you, everyone, for being here today. I'm here to introduce Peter Blazitz. Peter got his Bachelor of Science from the University of Vienna, as well as a Master of Science and a Doctor of Science from the University of Vienna. His supervisor during his PhD was Dr. Paul Winkler, and currently he is an assistant in the aerosol physics and environmental physics group at the faculty. He's a faculty of physics at the University of Vienna. This presentation is going to be about 45 minutes, and we'll have time for questions at the end. Peter, you can go ahead whenever you're ready. Thank you.
Thank you very much for the introduction. I'm going to start right away. So today I want to speak about a publication of ours from last year entitled Size Characterization and Detection of Aerosolized Nanoplastics Originating from Evaporated Thermoplastics. And just to make sure, I want to show you a screenshot of that publication. So we published in Aerosol Science and Technology, and you can see in the figure caption the full link to access the publication. It's open access, so everyone can retrieve. Okay, so let's get right into it. So I'm speaking about nanoplastics, so I want to introduce plastics first. And as you all know, like plastic products are ubiquitous in our daily lives. Like there is no way around handling and getting into contact with plastic products. That starts with cups, clothing, bottles, packaging materials, the keyboard in front of you, and so on, you name it. So it's everywhere. And the basis of plastics in general are organic polymers, and these organic polymers, macromolecules, are made up of repeating monomer units. And these monomer units that are repeated actually give the name of the plastics, as we see later. Why this class of material is so successful is because it's versatile. And that versatility also arises from the option to add chemical agents, and these chemical agents are called additives that can be softeners, that can be flame retardants, etc. And during the last decade, there was a rising demand for plastic products, and if these plastic products are not properly handled, there is also a problem with the rising amount of plastic waste, and that is especially valid for plastic-derived smaller entities, so-called micro and nanoplastics, that have been proven or shown to endanger ecosystems, wildlife, and also human health. It's important in this context to go with some sort of definition. There is a few definitions out there. For this paper, we decided to go with the following definition you can see at the bottom here. So microplastics are plastic-derived particles with diameters between 1 micrometer and 1 millimeter. Everything bigger you would refer to as macroplastics, and everything smaller with smaller diameters than 1 micrometer you would refer to as nanoplastics. So, as I said, that plastic waste and actually also the dispersion of plastics from the daily use is an increasing problem. And in recent years, there was an increasing number of studies that investigated the presence of these micro and nano particles coming from plastics in the environment. And I want to highlight here two things. As you can see, there was reports of microplastics in atmospheric fallout from cities. There's one exemplary publication from France, one other publication from China, and most interestingly or shockingly, these particles have also been found in sparsely inhabited regions far away from any civilization, so in a remote high altitude site in Austria, for example, or the Arctic. And all of that suggests that there is transport processes we need to take into account. And specifically, we need to take into account atmospheric transport as a pathway of these particles into remote regions. And so based on this, it is crucial to investigate all mechanisms mechanisms that yield any pathways into the environment. And that brings me to the outline of the publication. So summing that problem up, there is an urgent need for measurement techniques that are capable of detecting and also characterizing these aerosolized, especially nanoplastics. And the first necessary step in this, and also the first logical step, is to produce nanometer-sized particles from these materials in a reproducible and stable way, such that there is something like a plastic standard that we can use for instrument development, for example, or for testing if certain existing instruments are actually capable of detecting these particles. So as a result, we tried to find or tried to experiment with the reproducible generation of sub 40 nanometer aerosol nanoplastics using a common tube furnace, which is a quite common particle generator in our lab. We used common thermoplastics as particle materials. I'm going to speak about this in more detail in a bit, but there was higher purity versions and commodity versions. And one of the main aims of that study was to investigate the effects of the external experimental parameters like the temperature, setpoint temperature of the tube furnace, the flow rates, the amount of material on that particle generation. And with that, I want to speak about the experimental approach. So we employed a very common three-step principle that you see outlined here in this graph. So step one consists of seed particle generation. The second step consists of the charging of these particles, so bringing charged in a control layer onto the particle such that it can be size selected. And the last step is then the detection of these produced particles. We've been using for the seed particle generation a tube furnace, as you are going to see in a bit. Charging and size selection happened with a soft X-ray charger and a Vienna type nano DMA. I'm going to speak about DMAs in a second as well. And for the detection of these particles, we used the condensation particle counter and the Faraday cup electrometer. So condensation particle counter is based on the condensational growth of these nanoparticles within the instrument, such that these particles can be detected optically. An alternative way of detecting is a Faraday cup electrometer, which measures the current coming in, and the current is then proportional to the particle number concentration of the particles. So you can see this as a kind of backup detector for now. Yes, that brings me to the tube furnace. So here on the right side, you can see a sketch that I've been drawing of a tube furnace. It is actually a pretty simple instrument. So that's a tube that has heated walls. That heated walls are depicted here with the red color. And normally there is a ceramic working tube here in gray, and in that ceramic working tube, a quartz glass tube, in our case, the blue one, was inserted. And then the particle material is put onto a crucible that looks like a spoon and just inserted into the furnace. The furnace is then heated. So the furnaces in our lab by the manufacturers, they range from 30 degrees Celsius to approximately 1200 degrees Celsius. Luckily, we didn't need as high temperatures. And yeah, so it's based on the evaporation of the particle material in that crucible. There is a typo, it's evaporated, not evaporated. And the vaporized material is carried through cooler parts of the tube furnace, where homogeneous nucleation is initiated, and that's how the nanoparticles form. Then I thought it is important to remind everyone how a differential mobility analyzer works. So that's the instrument that we've been using for the size selection. You can again see a schematic here on the right side. And basically it is a cylindrical capacitor. So there is one electrode is in the middle here, that bullet-shaped electron. The other electrode would be the outer layer. And in between there is a voltage, so pretty simple principle also. And the performance of such a DMA depends on geometric parameters on the one hand, so the inner radius of that of that electrode, of that inner electrode, the radius R2 you can see there, that's the DMA radius, and then the length of the electrode. And on the other hand, it depends on the operating conditions, which is a set of flow rates depicted by the Q here. So on the left upper, you can see the sheath flow rate coming in. On the left lower side, you see the exhaust flow rate coming out. And the aerosol particles are basically carried through that QA, so the aerosol flow rate, and the sheath flow through that instrument. And these particles then, due to the electrical field and the previous charging process, drift according to their electrical mobility. So some particles, they might drift faster and hit the electrode. Some particles might not drift that much. They are then going out via the exhaust flow rate. And some particles just have the right electrical mobility such that they reach that exit slit that is depicted here and come out with the sample flow rate. And if everything is stable and symmetric and fixed especially, then there is a unique correlation between the voltage on the electrode and the electrical mobility. So this instrument then allows size selection by applying a voltage, and one voltage is connected to an electrical mobility equivalent diameter. Now, I want to speak about particle materials. As I already said, we used two groups of thermoplastics. So thermoplastics are plastics that in first approximation just soften if exposed to heat. So all of these materials are thermoplastics, and we had higher purity plastics and commodity plastics. Higher purity in this context means nothing else that it's just plastics of known composition. So we externally bought them. And we bought three types, as you can see: polyethylene, terephthalate, low density, polyethylene, and polypropylene. If these materials have been used for the measurements in the graphs later on, I put the P for pure as a superscript to denote it. And we had the same three materials also as commodity versions that we harvested from daily life products. So PET, as you all know, is used in water bottles, so we used a water bottle. The LDPE is coming from a very thin packaging foil, and the polypropylene we harvested from a common candy box. And here on the right side, you can see two pictures. Panel A shows the higher purity versions, so the pellets that we externally bought. The top whitish ones is the PET. The lower left one is the low density polyethylene, and the lower right one is the polypropylene. And as you can see, to harvest the commodity materials, a common standard hole puncher has proven to be a valuable instrument. So we just push it out and had this, what I call in the paper, platelets. Again, in the middle, the PET, lower left, the very thin LDPE foil. As you can see, that was already a bit challenging to cut it out. And on the right, the polypropylene. And with that, I think you have information enough that I can discuss the schematic for the full setup. So we can see here that we've been using compressed air as carrier gas. That compressed air was dried and filtered and then split between the tube furnace flow and a dilution flow. The compressed air was then passing the tube furnace, where the heterogeneous nucleation, the homogeneous nucleation occurs then. And in order to enhance particle production, we put a Liebig type condenser downstream of the tube furnace, which is basically just a glass tube that is flushed with cold water. Afterwards, we had the dilution flow mixed in if we needed it. Then it's followed by the charging process using a soft X-ray charger. Particles were passed into the nano DMA for the size selection. So after the tube furnace, the particles are polydispersed. After the nano DMA, we cut out the monodispersed slice of mobility diameters. The DMA had a closed loop sheath flow cycle, as you can see here. So the sheath air was again dried and filtered, and the flow rate was maintained using a critical orifice, so you can see approximately 24 liters per minute. And downstream of the DMA, the aerosol flow was equally split between the Faraday cup electrometer and the CPC. Since we didn't know what to expect, it made sense, since there is an upper and a lower detection limit for CPCs, to use a backup detector for the FCE that is not depending on the cutoff diameter or like a coincidence threshold. So it's just a backup detector. The curves I'm going to show in the following are all measured with a CPC. For those of you who are working with that kind of instrumentation, I put the full list of instruments here, such you can know which models we used. So we used two kinds of tube furnace. The main tube furnace was that Nabatherm furnace here that is mentioned, and the second one was a Carbolite tube furnace. As a charger, we used an advanced aerosol neutralizer 3088 manufactured by TSI. Then we had two custom-made Vienna type DMAs, one nano DMA, which we did most of the measurements with, and then we had some measurements with an extended diameter range. For this, we used the medium DMA, so you can see that length is different, else the DMAs were basically the same. Then the standard CPC we used was a TSI 3776. And for the cutoff measurements we needed a CPC with a bit higher cutoff, so we used the TSI 3772 and then a Modus 820. And the FCE in use was an aerosol electrometer, model 3068B, also manufactured by TSI. It was important to stick to a certain measurement procedure to be able to assess the reproducibility and especially the stability of the measurements. And that measurement procedure you see outlined here. And I want to discuss that briefly also. So the first step consisted of the insertion of such an empty glass crucible into the tube furnace and the adjustment of the flow rates. After that, we set a temperature of the tube furnace and waited until the temperature reading was stable enough. When this was the case, we recorded like 1 to 2 particle number size distributions to check for any contamination in the setup. So the expectation is, of course, if there is nothing in the tube furnace, no particles are detected, because no particles are produced. In case there was no particles, we inserted the particle material on the crucible and put it into the preheated tube furnace. In order to wait until particle production somewhat stabilized, we waited for 30 minutes. That is denoted everywhere as dwell time T0. And after all of that, we were ready to actually record proper particle number size distributions that were arising from the plastic materials. And that measurement procedure has been stick to for all measurements that I show. Well, and here, as you can see, it worked. I want to show some exemplary particle number size distributions here in two panels. In panel A, you can see the size distributions for the higher purity materials. Panel B shows the size distributions for the commodity materials. On the x-axis, you always see the mobility diameter arising from the use of the DMA. On the y-axis, you see the normalized particle number concentration that I call concentration from now on in both cases. And if we take a look at that panel A here, we see that the blue curve is corresponding to higher purity PET, the red curve is corresponding to higher purity LDPE, and it's distinctly different. I want to stress here that the size distributions can't be directly compared. You're going to see that in a moment because the settings were not exactly the same, but nevertheless it gives a good impression if one keeps that in mind, what to expect concerning the particle materials. In figure 7b, we see the blue curve for commodity PET and LDPE and commodity PP, as you can see, also slightly different. There is different positions of maxima, there is different onsets of the curves at the lower particle diameters, and there is also different width. So with that, I want to show you the experimental settings that curves are based on, just to give you for now an idea approximately how much the flow rates and temperature have been. So as you can see, if you look at the second column, so the tube furnace flow rate ranged from around 1 liter per minute to 1.6 liters per minute. The temperatures between 114 degrees Celsius and 200 degrees Celsius depends on the material. Already we can see already here though that the two PETs required somewhat more temperature, and LDP, the two LDPEs, somewhat lower temperatures to generate particles. Then I also put the masses, which is not so important now, but as you can infer, we used 1, 2, or 3 pellets, and depending on the material, the pellets had different masses. Then you can see the diameters that correspond to the maxima of the distributions. And there what's interesting to see is that the maxima of the commodity version and the higher purity version of the material is always more similar than the position of the maximum for another distribution of another material. So the two PET materials are centered, the maxima are around 10 nanometers. For the LDPEs, we see it's approximately 20 nanometers, and the PP we have 30 nanometers, so the biggest particles. And in the last column, you can see the 12 times. As I said, the 30 minutes we always waited, so that's right after that waiting time we took these PET-P distributions here and PET distributions. And if we waited longer, then you see, of course, times elevated or different from that 30 minutes. If you take a closer look at figure 7a here, you see that the higher purity polypropylene is missing. And the reason is basically shown in this plot here. So again, on the x-axis, you see the mobility diameter, on the y-axis, the concentration. And these curves correspond to that higher purity polypropylene for 3 different settings. So as you can see, there is different temperatures we tried, from 125 to 145 degrees Celsius, all just examples, different flow rates and also different masses. And it was not possible with that nano DMA to get to record the maximum. That's the reason why I took that polypropylene out of this plot, because it's somewhat, if we couldn't even see the maximum, there is not a lot of information. But the maximum is, I mean, you can just see it here, it's like 10, 20, 30, it's around 40 nanometers, probably even at bigger particles. So the next crucial step was, after we knew that there is particles produced, how stable are the size distributions? And that stability you can see in this figure 9 here. It's again on the x-axis, you always see the mobility diameter, and again on the y-axis, the concentration. Careful, it's all the time double logarithmic, so the differences sometimes appear a bit smaller than they were actually. And if we take, for example, figure 9a here, we see commodity PET at the temperature, tube furnace set point temperature of 180 degrees, and the different colors depict different dwell times. So the blue curve was measured 30 minutes after inserting, the red curve then 43, and so on. The green curve was the T0 plus 26. And what we see is that not just the maximum of the distribution decreases, but also it appears that the distribution somewhat gets slimmer. So it's narrowing down. So there is something happening that was rather a not so stable size distribution. On the other hand, if we look at figure 9b, which corresponds to higher purity PET, so the PET with known composition at a higher temperature, so 220 degrees instead of 180 degrees Celsius, and there we can see that all 3 curves measured at the same times actually overlap, so that distribution was stable. And since maybe I go back quickly, since we realized that here the distribution is cut off, we actually decided to also do measurements with that longer DMA, which allows a extended range of mobility diameters that can be selected. And on top, we also used a different tube furnace, the second one that I presented, such that we can see if there is any effects of the tube furnace. Maybe it wouldn't work for the other one or whatever. And here in this figure 10, again, you can see mobility diameter on X, concentration on the Y-axis, and 3 different higher purity materials. The blue curves correspond to the blue curve corresponds to the higher purity PET. So in case of PET, there was no need for a extended diameter range. As a result, we just put the nano DMA curve in here. But on the other hand, for the higher purity LDPE and the higher purity PP, it was necessary to use the medium DMA, and that's the curves that correspond to the red markers and the green markers. And what we can see here is that these curves, that concentrations here come down at around, let's say, 100 nanometers. And what we can also see that is starting from around 10, 20, 30, like, let's say 80 nanometers, there is also a coagulation effect appearing. But these measurements were just aimed at seeing how big the particles actually are that we are producing if the whole size distribution couldn't be recorded with the nano DMA. And with that, I want to discuss that first, or summarize actually, that first part of the talk, because I'm assuming that was a lot of information already. So we found significant differences between the particle number size distributions of all the thermoplastics in use. These curves differ not only in the steepness of the slopes, but also in the positions of the maxima and the covered diameter ranges. So some were narrower, some were broader. The smallest particles we could produce with higher purity PET and commodity PET. The largest particles were produced with the polypropylene that I showed at the end. Stable particle number size distributions in the available size range could be measured using the higher purity PET as particle material. And using that medium DMA, we could find out that the maximum diameters of these non-PET distributions, so the LDPE and the PP, is centered around 100 nanometers, which is the biggest particles we could produce at all. And based on this, we decided that higher purity PET is probably the best candidate to do further investigations, especially the investigations on the external parameters now, the tube furnace temperature, the flow rates, and so on. And that's what I want to present now. So these measurements have been done in the following way. So we always just changed. So the three parameters we wanted to measure, we wanted to investigate was the set point temperature of the tube furnace, the flow rate through the tube furnace, which was the QF, the amount of material, so 1, 2, or 3 pellets, or however many platelets. And the parameter of interest was changed, and all other settings we kept constant. And we measured always 3 curves. So which you can see here in figure 11 for the set point temperature. So again, mobility diameter on the x-axis, concentration on the y-axis, and every color or every curve or every color corresponds to a different set point temperature of the tube furnace. So in blue here, we used 160 degrees, going to the red one with 180 degrees, and then the highest temperature we've been measuring in this comparison was the green curve with 200 degrees Celsius as set point temperature of the tube furnace. And so the set point temperature T was just steadily increased by 10 degrees from the onset of particle generation. So when we could detect the first particles, we just went through the whole range of available temperatures. And here it's pretty obvious that there is something happening with temperature. So that higher temperature on the one hand is connected to a broadening of the size distribution. So if we compare actually red to blue, you can see it pretty nicely. They start approximately at the same diameter, but then the red one is way broader. So there is also more particles produced. On top, the position of the maxima shifted again, so not just in the height, but also on the diameter axis. And in the extreme case here of the 200 degrees, we can see that the maximum completely was wandering to higher, larger particle diameters. And also again, the broadening from the red one to the green one. Next, we did exactly the same for the flow rate. So we again used higher purity PET at a temperature of 200 degrees, as you can see here. And we used, in the figure description, we used one PET-P pellet and just adjusted the flow rates or changed the flow rates and recorded the size distributions again. As a short reminder, that QF that is depicted here in the figure is the flow rate of compressed and dried air that passes the tube furnace, not the dilution and not the flow rate through the DMA. So if I tell you that the flow rate through the DMA was constantly kept at 3.2 liters. If you subtract that furnace flow rate, you basically get the dilution flow rate that we've been using. And here we can again see significant differences, although I need to say that onset of the size distributions, that's probably not significant, so that's actually pretty robust here. And the same in the uncertainties, but what we can see again is the positions of the maxima, and also with increasing flow rates we see a narrowing of the size distributions, which is pretty interesting, and is probably linked to the fact that with higher flow rates there is an enhanced surface cooling. If you think about that pellet on the crucible in the tube furnace, there is just more flow passing through, so there is probably cooling which is somewhat impeding particle production. The last parameter we investigated is the amount of material, and also, as you can see here, without making it, I can make the short, like the amount of material also influences the shape of the particle number size distribution as expected. On the x-axis here, again, the mobility diameter, y-axis the concentration. The different colors of the curves correspond to a different amount of material. In that case, it was again higher purity PET. So 0.25 grams is approximately one pellet. So we have size distributions here for 1, 2, and 3 pellets. Exactly, and the tube furnace flow rate in this case was kept constant at 1.6 liters, and the distributions were measured at 200 degrees Celsius. And what we can see is that increasing the amount of material in general, and that's really intuitive, yields higher particle number concentrations. They are also somewhat broader. So we also observe again that broadening of the distribution and also the shift of the maximum diameter. So more material shifts the position of the maximum towards larger mobility diameters. As you can see, if you compare the blue curve to the red and the green curve. And then, as last comparison, we were able to actually directly compare that higher purity PET to the commodity PET, which was pretty interesting. So that's depicted here in figure 14. The set point temperature for the tube furnace was 200 degrees Celsius, and the flow rate through the tube furnace was 1.6 liters per minute, and we used 0.05 grams of material, which is the equivalent of 2 pellets in that punched out platelets. And so these two curves now can be directly compared. What we see is the maximum of the higher purity PET is centered around 20 nanometers, and the maximum of the commodity PET in red is centered around 10 nanometers. So the position of the maximum is completely different. Then if we compare the curve corresponding to the commodity PET to the curve corresponding to the higher purity PET, we see that there was way more particles produced with that higher purity PET. So the blue curve is way broader than the red curve. And interestingly, or just for completeness, I want to say that we did that measurements also for different temperatures, different set point temperatures, and what we found is that the difference between the two materials is actually diminishing with increasing temperature. And that is somewhat it doesn't really point, but it's a hint for additives. So it could be, or one possible explanation here would be that the commodity PET is actually, there is actually some flame retardants or something in there as additives that somewhat impede particle production. That's what this plot could show. So with that, I want to summarize the second part of the results. That was the effects of the experimental parameters. So we assessed the impact of the set point temperature, the tube furnace flow rate, and the amount of material on the particle number size distributions of higher purity PET. We tested approximately 35 combinations of settings, where you just seen the combinations where you see a proper difference, like concerning the scaling. All three parameters have shown to significantly influence the concentration of the produced particles and especially the diameters of the produced particles. There was no significant differences between the onset diameters of the two materials, so which you can see here. So they are basically, the blue and the red curves is more or less on top of each other within the measurement uncertainty, for sure the same. And the direct comparison, as I already mentioned, points towards the use of additives like flame retardants in the production of commodity PET. Along these measurements, we've seen a discoloration of the material, which I show here on this slide. So it's titled Exposure to Thermal Stress. So in figure 15a, you see that whitish pellets. That's just pristine pellets as we inserted them into the tube furnace. Panel B shows the same pellets after experiments at 200 degrees Celsius. And panel C shows one of these pellets after experiments at a tube furnace set point temperature of 220 degrees. So now the figure, of course, suggests that it just depends on the set point temperature of the tube furnace, but I want to stress here that that's a time that there is also a time component that needs to be taken into account. So after some time at 200 degrees Celsius, the pellets start turning brownish, and after very many measurements and a long time at 220 degrees Celsius, the pellets actually start to melt in a bit and get really dark. So this is, as I would say, probably a hint for some kind of oxidation process, but we don't know for sure with the instrumentation that we used. Now I want to go to the last part of the measurements, which was the 50% cutoff diameters for some of the materials. And here I want to do a short introduction also. So the detection performance of condensation particle counters is commonly quantified with the 50% cutoff diameter that is denoted here by D50. That cutoff diameter is calculated in the following way. So we put the particle material into the tube furnace and get particle number size distributions for the CPC on the one hand and for the FCE on the other hand. And if these particle number concentrations, capital N, are divided by each other, so the CPC divided by the FCE, you get the detection efficiency. And that detection efficiency goes from 0% to 100% or from 0 to 1. And at the point where the detection efficiency equals 0.5 or 50%, the diameter that corresponds to this point is the 50% cutoff diameter. So the particle diameter where 50% of the particles coming into the CPC are detected in first approximation. And we were able to also do these measurements, and the results you can see in table 2 here. So the first column, you can see the material, which was higher purity PET and commodity PET. Second column shows the CPCs we used, and the third column shows the cutoff diameter. So if we, for example, take now the TSI 3772, then we see that for the higher purity PET we got a cutoff diameter of 7.4 nanometers. For the same CPC but commodity PET, that's the lower part of the table, we see that we get exactly the same cutoff diameters, so 7.4 and 7.4. And in case of the Amodus A20, for the two materials, we get 4.6 and 4.4. So within, as you can see, the uncertainties here in the brackets, within the uncertainties, there was no difference in the cutoff diameters. And for this, I also have a plot. So the table that I've just shown is basically figure 16b. So here you can see on the x-axis the cutoff diameter for higher purity PET, on the y-axis the cutoff diameter for commodity PET, and the symbols and the colors correspond to the two CPCs. So red corresponds to the A20, green corresponds to the TSI 3772, and as you can see, there is no significant difference between these between the two materials, right? Since it's on the line, that's all good. Figure 16a now shows actually a comparison of these 50% cutoff diameters with previous measurements that I've done some time ago. And this plot shows on the x-axis different seed particle materials that we've been using. So sodium chloride, oxidized beta-caryophyllene, then we have the higher purity PET from these measurements, and silver. And on the y-axis we see the 50% cutoff diameter. And these cutoff diameters for these materials we've been measuring also with the two CPCs that we've been using for the plastic cutoffs. And what we can see here is that the cutoff diameters of the higher purity PET is somewhere between the cutoff diameter of the oxidized beta-caryophyllene and the silver in two butanol based CPC, and pretty far away, way lower than the 50% cutoff diameters for sodium chloride as salt in a butanol based CPC. So that also gives information about the composition of the material, if we think that the composition and the VEPA, that there is a favorable and non-favorable interaction. So in butanol based CPCs there is rather favorable interactions for these plastic particles. Yes, with this I want to wrap up also the cutoff measurements. So we've been measuring 50% cutoff diameters for higher purity PET, and these yielded diameters very similar to the measurements with oxidized beta-caryophyllene in a butanol-based CPC. We didn't see any significant differences between the 50% cutoff diameters of higher purity PET and commodity PET. After some time, material discoloration appeared, but we tested that material discoloration did not have any effects on the measured 50% cutoff diameters. So it doesn't really make a difference if you use the pristine white pellet or if you use the already darker ones that have already been in the tube furnace. And concerning that favorable interactions and non-favorable interactions, we can say that these plastic particles appear to be very different from the sodium chloride particles, so the activation is also very different. And this brings me to the limitations of this study that I want to outline here. So any effects, if you read it together with me, any effects linked to the shape of these pieces and of particle material were not investigated. It's also pretty difficult to assess whether the position of the particle material on the crucible is exactly on the same spot. And also the differences between particle production using pellets or platelets or just cutout strips cannot be excluded. Furthermore, we couldn't do detailed investigations of higher purity and commodity polypropylene due to the diameter range of the produced particles, as you've seen. Higher purity LDPE and LDPE, commodity LDPE, posed a significant challenge due to a pretty strong dependence on the dwell time, and that also yielded frequent shifts of the particle number size distribution. So it was not really that reproducible, to be honest. Another severe limitation is that set point temperatures well above the melting points and crucibles that were really filled, fully filled, yielded contamination of the working tube within the tube furnace. So what happens is, if the melting point is exceeded too much, the material basically melts down and starts cooking, and there is droplets everywhere, and then the whole glass is stained and needs to be heated to very high temperatures such that we can get it clean again. And in general, I want to state that the use of macroplastics as particle material for that kind of experiments requires a close monitoring of potential contaminations of the glass parts. So it's inevitable to use that measurement procedure that I presented. So just to always check if there is contamination in the glass parts, on the glass parts or not, prior to any measurements. This brings me to future research. So it is pretty obvious that these characterizations that we did can be extended to different plastic materials. So, to other plastic materials that we didn't test. For example, high density polyethylene, that's pretty interesting, probably the comparison to low density polyethylene, and also PVC, you name it. There is many other plastic materials. What is absolutely needed is a thorough chemical characterization of these produced particles. It's would be very interesting to see what these particles are exactly composed of. If the color, this discoloration changes the composition, etc. Then there should be studies of heterogeneous nucleation on these plastic-derived seeds. You see a check mark there in the bracket because we, in another publication, started this already, but there is also quite some work to do in this direction. And in the end, the characterizations of nanoplastic particle activation in CPCs based on different working fluids, so the prime examples would be water and diethylene glycol, should be investigated as well, such to get more information, would also yield passive information on the composition of these particles by the activation. Yes, so the time, yeah, that's fine. So I want to summarize. Our results demonstrate that aerosolized nanoplastics can be generated from thermoplastics using a common tube furnace. The set point temperatures we've been using range from 110 degrees Celsius to 220 degrees Celsius, and that yielded, depending on the material, particle diameters between 2 nanometers and 40 nanometers with the nano DMA, and up to 80 nanometers with the medium DMA. So in general, you can say that the particle diameters ranged from 2 to 80 nanometers. As I pointed out, this method requires close monitoring of the glass parts. The two LDPEs and the two polypropylene materials were pretty difficult to control, and higher purity PET turned out to be the best candidate for that kind of measurements, which yielded stable particle number size distributions at 220 degrees after 30 minutes of dwell time. And in general, the stability of the particle output improved with increasing temperatures and longer dwell times. So I want to conclude. This method can be used to generate plastic-derived nanoparticles, even plastic-derived sub-10 nanometer nanoparticles at high concentrations and comparatively low temperatures. If you compare to silver with around 1000 degrees Celsius, it's pretty low temperatures. Higher purity PET and commodity PET in particular have proven to be a valuable addition to the set of seed particle materials that are commonly used for calibration measurements. And that makes a defined aerosol nanoplastic particle source available, which should enable quantitative studies of heterogeneous nucleation and the ice nucleation ability. And that at some point could yield direct insight into the impact of nanoplastic particles on cloud formation. So to conclude, generally, we hope that we deliver the basis for further investigations toward a thorough understanding of the generation, dispersion, and toxicology of plastic-derived nanoparticles. And with this, I want to close the talk with some acknowledgements. I want to thank the AAAR Endowment Committee, the Aerosol Science and Technology Editorial Office, the Early Career Committee, and all people involved in the organization of this event for the invitation and organizing. I want to extend that thanks to my former PhD supervisor, Professor Paul Winkler, who also had the idea for these measurements, and my former research mentor, Paulus Bauer. I want to acknowledge my co-authors, Andrea Stöllner, Gregor Lattner, and Clara Magauer, who helped massively with the measurements and also were involved in writing the publication. And finally, I want to say thank you to the Aerosol Physics and Environmental Physics group here, where I performed these measurements. So thank you very much.
Thank you, Peter, for that very interesting presentation. Now we have about 10 minutes for questions. So I can start off with the questions in the chat, and then we can go to the audience after. So the first couple questions are about the, did you make any measurements regarding the chemical structure of the particles you produced in this study?
No, we didn't do any chemical characterizations yet. That is one of the biggest things that should be addressed during future research is chemical characterization.
Okay, thank you. The next question. Is the idea or assumption that these measured nanoparticles are released as a whole during the cooking, or that they are sublimated and recondensing in the airflow before the SMPS counts them?
So the expectation is that the particle material in the tube furnace is evaporating, and then particle formation is induced. So there is change here.
Okay, thank you. In terms of distribution broadening, is it based on the geometric standard deviation, or is it approaching the asymptotic value from coagulation?
For the big ones, I would suspect it's, wait if I can hear. As you can see between the red curve and the green curve, the coagulation effect is massively increasing. So I would say the limiting factor here is probably coagulation, definitely. Yeah.
Okay, thank you. Next question. How do the authors relate the tube furnace nanoparticle release of nanoplastic mechanism to those occurring naturally? Above, it is critical to see the changes in chemistry as a result of these mechanisms. Perhaps this is work you are planning.
Yeah, so I absolutely agree with the chemical characterization, as we already said. And I think on a bigger picture, and maybe also with natural release, I think that quite a lot of research currently is focused on the formation of debris. So it's cracking down of macroplastics into smaller and smaller pieces. And as you know, at some point, the van der Waals interaction is getting quite dominant. So there is a lower size limit to this. And I think that's why it's important that we use, or that we also expect that thermal stress of any sort as a particle source. And with the difference of that breakdown of macroplastics, this thermal production route seems to be way quicker. It's almost instantaneous. So what I would think here is about anything that's getting warm, I don't want to lean myself out too much, but for example, brakes at cars. I think such temperatures would be probably enough already. But there has been already reports or a very nice paper about the really daily life application, which is 3D printing. So the colleagues were able to measure nanoparticles just from a 3D printer.
Okay, thank you. Next question. Somebody is curious about the shape factor of the resulting particles.
The shape factor of the result. Yeah, so in the calculation of the electrical mobility diameter, there was no shape factor included.
Okay.
So spherical.
How environmentally relevant are nanoparticles produced in this way? Is vapor condensation an observed route to plastic aerosolization in the atmosphere?
That's to be investigated.
Okay.
What I can say at this point is we were able to activate these particles in water vapor already.
Mm-hmm.
Yeah.
Okay, thank you. That's all the questions in the chat. Feel free to add more while we go to the audience. I see one person with their hand up, Mr. Reinhard Niesner. Go ahead and ask your question when you're ready.
Yeah, thank you. So, Mr. Vlasic, thanks for this very detailed description of your experiments to produce nanoplastics. I mean, finally, you stated correctly that you produced some plastic-derived particles, but of course, the Scheibel-Postendorfer arrangement is never applicable to produce a nanoplastic, since you are changing the chemical composition all the time. And what you observed so far is really a partial degradation, a thermal decomposition of the plastic material. So I really like to exclude the Scheibel-Postendorfer approach to produce nanoplastics. You have to have a very instantaneous procedure, which, for example, lifts material from the surface immediately. For example, we did it with femtoseconds or nanoseconds lasers.
Lasers, yeah. Mm-hmm.
So you cannot apply these temperature increasement and so on. So you are certainly not aware of all these analytical approaches around the microplastic and the nanoplastic, which took a part of my career in the last years. You will find really numerous papers on, for example, the Curie point gas chromatography for characterizing polymers.
Mm-hmm.
They make exactly the same as you, only within a gas chromatograph. It's exactly the same. And and there are other applications reporting on the harmful exhaust created by plastic pyrolysis.
Heating, yeah. Mm-hmm.
A phone call of Gunther Oberdörster from Rochester, who asked me what happens with Teflon. If you simply heat up Teflon, you produce a chemical warfare aerosol, a submicrometer, your nano aerosol, but of completely different position. And it's very dangerous. So what you are presenting here, yeah, that's the view of a physicist, quite clear. So what you need are chemists. And I mean, last year I was in your institute and I lectured about chemical characterization of aerosols.
I remember at the summer school, you mean, right?
Yes.
Yeah.
We applied, of course, Raman spectroscopy, and even for nanoparticles, we levitate these nanoparticles within laser beams. And so there are so many attempts to do that, but you selected exactly these way, which a chemist always would avoid.
Because it's changing. I get your point. Yeah, I get your point.
Okay, then I stop. Thank you.
Thank you very much. Very interesting. Yes, very interesting.
Okay, thank you, everyone. If we have any other questions from the audience, feel free to unmute yourself and ask right now. Otherwise, we can end this lecture here. Okay, seems like that's it for us. I'd like to thank Peter again for this very interesting presentation. Thank you for all of the audience for joining us today, and thank you for all of your questions. Have a wonderful rest of your day, everyone.
Thank you.
Bye-bye.